Hello everybody and welcome back to chapter 3. In this video we're going to go over section 3.2, which it has to deal with logarithmic functions and their graphs. So 3.1 was exponential, so now we're going through their inverse functions, logarithmic functions. So what are our objectives? We're going to recognize and evaluate logarithmic functions with base A. We're going to graph. We're going to talk about the natural log, and then we're going to use logarithmic functions to model and solve problems. Okay, so then let's see here. So every function of the form f of x is equal to a to the x, we just said in 3.1 that it passes the horizontal line test and therefore has an inverse. So the inverse of that is called a logarithmic function with base a. So remember what it means for a function to have an inverse. It means that a couple of things. The input becomes the output, and vice versa. The output becomes the input for the other function, okay? So, so basically, if you think about for x positive and a positive and a non-1a, the logarithmic is defined as y is equal to log of base a of x if and only if x equals a to the y power. So what does that mean? That means if you have an exponential function, so notice that the logarithm is the exponent. So y is the logarithm. Okay, so you can read this: f of x is equal to log base a of x. It's called the logarithmic function with base a. So these two equations are equivalent. So if you see one, you can automatically assume that the other exists. The first one is logarithmic form, and the second one is called exponential form. So let's say, for example, if 2 is equal to log base 3 of 9, then you can also say that 9 is equal to 3 squared, which is true. And if you have 5 cubed is equal to 125, that's equivalent to saying log base 5 of 125 is equal to 3. So when you're evaluating logarithms, remember that a logarithm is an exponent, right? That means that log base a of x is the exponent to which a must be raised to obtain the x. So in other words, log base 2 of 8 is equal to 3 because 2 raised to the third power is 8. So see how the logarithm equals 3, and then 3 is the exponent in this situation. So let's evaluate a couple of logarithms. Okay, so let's say you have f of x is equal to log base 2 of x, where x is 32. So f of 32 is log base 2 of 32. But what number do you need to raise 2 to become 32? So you can do this a couple of ways. We know that it's 5 basically, because 2 to the 5th power is equal to 32, therefore the solution is 5. Okay, so in this case, log base 3 of 1, okay, what's that equal to? Well, 3 to what power equals 1? And that power has to be 0, because any number raised to the 0 power will equal 1, okay? So for C, log base 4 of 2. So 4 to what power is equal to 2? Well, the power that 4 needs to be raised to is 1/2, which is square root of 4, which is 2. So if you have log base 10 to the 1 over 100, 10 to what power equals 1 over 100? Well, 10 to the negative 2 power is equal to 1 over 10 squared, which is 1 over 100, which is what we wanted. So the exponent is negative 2, so therefore the logarithm has to equal negative 2. Cool. So let's go into some super fun properties, right? So the logarithmic function with base 10 is called the common log. You can either see it as log base 10, little tiny 10, or just log. When there's nothing written, the assumption is that it's 10. On the calculator, most calculators, the function is defined by just this log. I mean, it's expressed as this log. So here are some properties, okay, that follow from the direction. So from the definition. So log base a of 1, any base log of 1 will equal 0 because any number raised to the 0 power is equal to 1. When the base and the argument match, so log base a of a, that's equal to 1 because a to the first power is equal to a. So if you have the base matching this number, the big number, or whatever you're taking the log of, then you know that that's 1. Okay, so log base a of a to the x, that's going to equal x, because a to the log base a of x will equal x. So another way you can think of it is base a to the power x will equal a to the x. That's another way to think of it. So these are also true. These are both true properties. So if you see log, the bases match, but then you have an exponent here, that's going to equal that exponent. And then here, if you have the bases match here, that's just going to equal the argument. Okay, so then now if you have two logs with same base that are equal to each other, then you can assume that their arguments are also equal. And this is called the one-to-one property. So we notice that there was the one-to-one property for exponents, and this is the one-to-one for logarithms. So let's talk about the graphs of logs. So to sketch the graph of y equals log base a of x, remember that the graphs of inverse functions are reflections of each other over the line y equal x. So let's see here. So in this coordinate plane, let's sketch the graph of each function. So I'm going to show you how to do this in your calculator because you have to do something special to do the base of log right here. So I'm going to show it to you. Let's see here. So let me quit that. So y equals, okay, and the first one you're going to enter 2 to the power and then the x key, okay, and then leave that. And then for y2, you have to hit log. Where's log? There it is. Log of x, but since you can't, notice that you can't use the base, so we do, and we're going to get into this more later, but just to see it in your graph, you have to rewrite this as a ratio of 2 logs, and this is called change of base rule, but we're going to get into it in the next section, but just to graph it, you can see. So that's the graph of log base 2 of x, and notice that they are, I'm just going to zoom in a little bit so that I can see, or maybe I'll change my window. If I change it back to 10, that'll give me a better picture of it. Okay, see, there you go. So yeah, so now it's reflected across the line y equal x. Another thing is let's say we wanted to construct a table of values. So if you wanted to do this the plotting way, remember that after you graph it, you could hit a second and then the table, which is above the graph, which is the graph button basically, and it'll show you a table. But if you wanted to do this by hand, that's also totally fine. And if you constructed a table by hand, then you could plot the points and then you would see for yourself that's what the log is. You can first do y equals 2 to the x, right? And then find those. And then you can see that the logarithm, the inputs become the outputs and so on. So basically, log base 2 of 1/4 will be -2. Log base 2 of 1/2 will be -1, and so on, because they're inverses. Log base 2 of 1 is 0, and so on. Okay, log base 2 of 2 is 1. Okay, so that's that. They're inverse functions, and that's how you're saying we can also notice that they are a smooth line. We could graph them by just flipping y over y and the x values, and notice again that there is symmetry. Okay, so in general, the logarithmic function looks kind of like this. Kind of does this kind of deal, because this is the nature of the graph. Okay, so here, this is kind of typical. They have one x-intercept and one vertical asymptote. So the asymptote would be the y-axis, or x equals 0. And notice how slowly the graph rises. Okay, so this is the basic. So here's some basic characteristics in summary to sum up everything that we've talked about. So you have the graph of y equals log base a of x for a greater than 1. The domain will be from 0, not including 0 because it's an asymptote, all the way to infinity. The range goes from -infinity to +infinity. So all this. The x-intercept will always be 1, 0 because log of 1 is 0. It's always increasing, and it's 1-to-1, so it has an inverse function. What else? The y-axis is a vertical asymptote. It's continuous. And it's the reflection of the graph of y equals a to the x about the line y equals x. So remember that the basic characteristics of a to the x, this is from last section. So remember that a to the x had a domain of negative infinity to positive infinity, and the range was 0 to infinity. The y-intercept was 0, 1, and then the x-axis was the asymptote. So notice that these are like the, not opposite, but they're the inverse of this. Okay, so this is the range of log, this is the domain of log, this is the range of log, and so on. And the intercept is 0, 1, 1, 0, and so forth. Okay, so let's talk a little bit about natural logs. What is a natural log? Okay, so remember that e to the x is 1 to 1 and has an inverse function, and we talked about that it's a special case of a to the x. Well, just how e to the x is a special case of exponential functions, we have a special case of logarithmic functions that have base e. Okay, and we use this called we call this the natural log of x, or ln of x. Okay, so we write this without a base. The base is understood to be e. So basically, I'm saying base a lot. Okay, so if you look at this, the function f of x equals log base e of x, and we don't really write this. It looks kind of weird. It looks like I'm writing logix, right? It doesn't. We just decided that we're going to get rid of this log base e, and we're just going to replace this with the word natural log, ln of x. This is how we say it. We don't say ln x, we say ln of x. And that's for all positive x. And this is the natural logarithmic function. So honestly, it has all the same properties that logarithmic functions do because it is one. It's just a special case. All right. So they're inverse functions of each other. And ln of x and x equals e to the y, they're equivalent, right? So if you have y is equal to ln of x, you also know that x is equal to e to the y. All right, so then here's the graphs, and you see that there's that symmetry across the y equal x axis that we love, right? Notice here that you have 0.01 on e to the x and 0.10 on ln of x. And for x equals 1 on e to the x, you have the 0.1 comma e. And for ln of x, you have the point e comma 1. So it's basically, they're just mirroring, yeah? So you can kind of see they have the same properties of all logarithmic functions. This is the, the asymptote is, the vertical asymptote is the y-axis, or x equals 0. It grows this way. And it's useful. It's super useful. So it's actually in most calculators as well as ln. Okay, so how would we use a calculator to evaluate ln of x at these values? So really all you have to do is just hit ln and make sure that you enter the calculator. Now some calculators, if you don't have a TI 83 or 4 or plus or 89 or whatever, and it doesn't let you enter it in, so like say, I think the iPhone calculator, you have to push 2 first and then ln. So you're going to want to mess around with that. Here, notice that ln of -1, it gives you error because it does not exist. Okay, if you remember, the ln function does not have anything on to the left of the y-axis. Okay, so some properties of logarithms. For the natural log, it's the same thing as regular log or common log. If ln of 1 is equal to 0, since e to the power 0 is equal to 1, ln of e is equal to 1 because e to the power 1 is equal to e. The inverse properties, which is ln of e to the x is equal to x, and e to the ln of x is also equal to x, and then the one-to-one property. Oh, and this is an L, I'm sorry. This should say proper T, not properly. Properly. So if ln of x is equal to ln of y, then we can say that x is equal to y. Great. So that's all I have for 3.2. This is your super fun homework, and I will see you on the next video. Happy studying.